A very good evening to the students of class 12. Let us continue the curriculum with chapter number 3, that is current electricity. We have completed the chapter number 1 and 2. You can see it in my channel, that is Physics with Danu Saraiya at the YouTube. So now we shall continue our chapter number 3, in which we are today discussing how does electric current flow in a conductor. We have always learned in our yesteryears that the current flows in a conductor through a conductor by the motion of the electrons, right? Now we have to understand how there is a continuous flow of the electrons in a conductor. That is the topic which we are talking about right now. Then we will discuss about the definition of current, Ohm's law and limitations of Ohm's law in this video. So keep watching till the end so that you understand these concepts very clearly. Okay, so now let us talk about electric current in a conductor. Consider one conductor in which there is no electric field created. Here we have a diagram of a cylinder which is considered as a conductor. At present, let us think or understand that there is no electric field in the conductor. If there is no electric field, then what happens to the electrons? The electrons will drift. They will collide with the ions that are immovable, static in the conductor. After collision, the speed will be same as before collision. That is, the direction of the velocity of these electrons will be random direction. Random direction. Therefore, on an average, number of electrons traveling in one direction are equal to the number of electrons traveling in exactly the opposite direction. Therefore, the net current is equal to 0. This happens when the electric field is 0 in the conductor. Okay. Now let us consider that the electric field is non-zero in the conductor. Fine. Now let us apply an electric field to the conductor. Fine. By placing two dielectric discs on its plane surfaces and charge these discs, one with a positive charge and the other disc with a negative charge. So as soon as we place these charged discs on the surfaces, plane surfaces of the cylindrical conductor, there will be an electric field in the direction of the positive plate towards the negative plate of the conductor. Okay, positive charge towards the negative charge, and due to this electric field, the electrons will be accelerated in a direction opposite to the electric field as shown here. Okay, from the negative charge to positive charge, and there will be a current in the conductor shown. Okay, now this current will be temporary till the electric field is available due to the presence of the charged disc or plates, and the electrons which are flowing will keep neutralizing the plates. So what are the electrons doing? They are neutralizing the charges on the plates. So once all these charges gets neutralized, there will be no electric field. So there will be no electron flow. So there will be no current. So the current will be available in the conductor for a certain period of time, and then it will vanish away. Now, to have a continuous current in the conductor, we must have a mechanism which will continuously supply the charge positive on this plate, the charge negative on this plate, such that there is an electric field from positive charge towards the negative charge disk, and there is a flow of the electron opposite to the electric field, and the current keeps on flowing in the conductor, which is possible in a cell or a battery. Fine. So there should be a mechanism for continuous supply of charges on the disc or the plates which we have attached at the two ends or the surfaces of a cylindrical conductor. So in this way, there will be a continuous flow of charges in the conductor such that we get a continuous current. Fine. So this is the concept to understand how there is a continuous flow of the charges. Therefore, how there is a continuous flow of the electric field in a or electric current in a conductor. Fine. So take a pic and understand the concept very clearly. In the next page of the same video, we shall discuss or we shall state the Ohm's law, which is related to this flow of electrons and hence the current in the conductor. Fine. Please take a pic. Now, the net amount of the charge that flows through the conductor can be written as Q is equal to Q plus minus Q minus, and the flow of the charge is in a positive direction. If electrons are in the negative direction, then the flow of the current is in positive direction. For steady current, we have this charge directly proportional to the time of flow such that we get I is equal to Q by T. Fine. So now we define the current and we consider delta Q is equal to the net charge flowing through the cross section of the conductor in a time interval of delta t such that the flow of the current is given by limit delta q upon delta t. Fine. Okay. The unit of current is amperes. Okay. Now, as said in the previous page of this video, there should be a continuous energy such that we continuously supply charges to these plates or the disk, and we get a continuous flow of the electrons in the conductor such that we have a continuous current. So now let us state the Ohm's law. If we have I is equal to the continuous current across a cross section area of the conductor, and V is the potential difference between the disk or the plates of the conductor, then V is directly proportional to I such that V is equal to IR or RI, where R is the proportionality constant called the resistance of the conductor, where R depends on the dimensions and the material of the conductor. Okay, and its unit is ohm, denoted by the symbol ohm. Fine. Okay, so here we have stated the Ohm's law, which states that the current is directly proportional to the potential difference, and hence V is equal to IR, where R is a constant of proportionality depending upon the dimension and the material of the conductor. Fine. So I hope you have understood this concept, and in the same video we shall move to the next page where we shall discuss about the limitations of Ohm's law. Fine. So take a pick and understand this concept very clearly. Now we understand the limitations of Ohm's law. Let us go to the first limitation. Before that, let us rewrite the Ohm's law as the formula and the proportionality, which states that the potential difference is directly proportional to the current. Fine. Okay, which means if we draw a graph between V and I, it should be a straight line starting from the origin. It is always like that, but as the current increases, V ceases to be proportional to I. What is the first limitation? V ceases means stops to be proportional to the current. So, under normal conditions, we must get a straight line graph Instead, we get a straight line up to certain limit, and then the proportionality ceases away, means goes away. V ceases to be proportional to I as the value of the current increases, and we get a different shape of the graph. This is the first limitation of Ohm's law. Fine. Now we move to the second limitation of Ohm's law. Ohm's law, the proportionality depends on the sign of V. Okay. So let us consider the graph here with O as the origin. This side is a positive potential, this side is a negative potential. So as per the law, we have to get the same shape of the graph, whether the potential is positive or whether the potential is negative. But it is observed that the shape of the graph for the positive potential is in this type, keeping the value same for V, magnitude same, but the symbol opposite, we should get the same values for I, and the shape of the graph should be same but in opposite direction, but that does not happen, and this is what we get as the shape of the graph for the negative V, keeping the magnitude same but the symbol or the sign opposite. This is the example of a diode which behaves or which has this type of a characteristic, that keeping the magnitude same for the potential, we get different values of current when the sign of V is changed or reversed. Fine. And we should have got the same kind of a graph, that is this way, but we are getting a different shape of a graph. This is a limitation of the Ohm's law, which does not give us the same magnitude for the current when we change the sign of the potential. So I hope you have understood both the limitations 1 and 2. Take a pic. In the same video, in the next page, we shall go to the limitation number 3. And remember, here we have taken the graph or the example of a diode which behaves like this. Fine? Okay? Take a pic. Now we move to the third limitation of Ohm's law, which states that the relation between V and I is not unique. What is the meaning? That for every value of V, we must have one single value of I, but that is not the case. There are certain materials like semiconductors in which for same value of I, we have different value or values of V. Fine. This happens in semiconductor. Example, gallium arsenide, denoted by GaAs. Gallium arsenide. Fine. Okay. So let us plot a graph for Ohm's law for such an example in which the x-axis is V and y-axis is the current, where we have divided the graph into three sections. One portion goes linear, then the linearity loses, and then for the same value of I, we get different values for V. So first let us label the sections. This is showing the non-linear relation between V and I. Okay, between V and I. This portion is showing us negative resistance region, and this portion is the linear region between V and I. Okay, this is an example of gallium arsenide. And what is the limitation here? You can see for the same value of I, you have approximately different values of the potential, which is a limitation of Ohm's law. We must get I proportional to V, which is not the case in the whole graph for a semiconductor. Fine. So understand this concept that the limitation is we get different values of the potential for the same value of current. Okay. So I hope you have understood this concept also. Take a pic and understand the concept very clearly. Note down especially the regions, because these regions are asked in the exam, whether it is an entrance or whether it is a board exam. Fine. The regions are not labeled and those are the questions. Fine. Okay. So understand the regions very clearly. Take a pic of what we have done just now or understood just now.